David, hello everyone again. Don't worry, I'm not having another lecture today. You're spared pardon for today. But I have an utmost pleasure to chair my very good friend and colleague Maciej Cytowski, who is a scientist at Supercomputing Center in Warsaw, ICM. It stands for a very long Polish name, which translates to Interdisciplinary Center for Mathematical and Computational Modeling. What a better place to actually do computational cosmology, I guess. But Maciej is actually dealing with all the computational sciences, not only cosmology, as a very good expert. And he will give you a lecture today introducing us, all of us, to supercomputing, computing on supercomputers, including some practical information, I believe, for the workshop as well. Without further ado, I give the stage for you, Maciej.
Thank you, Wojtek, for the introduction. So we met with Wojtek because Wojtek is one of the users of our supercomputers. So that's the connection between us, and I'm supporting, at ICM, I'm supporting researchers that use our supercomputers to do the research, also cosmology, astrophysics as well. And today, this lecture will be some kind of an introduction to the things that we'll do later on during the workshop, because the main plan for today for all of you is to learn how to use those supercomputers. At the beginning, at some toy examples, toy applications. So how to run jobs on supercomputers. You will have access to the system which is right here, which is the biggest system that ICM has. I will start with an introduction of ICM, but that will be very, very short, just to give you an idea that actually all of you can access those supercomputers with no problem if you have a proper research idea, proper research project to go and you can try to submit proposals to ICM and to other computing centers in Poland or in Europe, because there are many places like ICM all around. Also in Krakow, there is one center that is doing pretty much the same. Then in the second part, I will introduce the supercomputer that we'll use during the workshop. It will be a brief introduction, I would say. I have a couple of slides, but maybe some of them I will skip, because just to give you the main ideas of how these computers are built and what is the main reason that or the main things, the main features of those computers that we should be aware of. And then at the third part, we will start the let's say, technical description of what you should know about the tools that are installed there on the supercomputer that you will use to run your jobs and you will use to do science, actually. So these are basic tools that you will have to get to know. Okay, so as I said, ICM is a supercomputing center. So it provides services of large-scale computation, analytics, something which is very famous, the big data analytics. Also data visualization, and we serve for scientific users. Scientific users can use our resources without paying for this, so you can apply for resources and use them. You can also get support from computer scientists that will help you to use those supercomputers, and also other things that are at our center. And that's a place where you usually can start an interesting project, which also might be a project in cooperation with ICM. That's what we have been doing with Wojtek for many years. We have been running many very, very large cosmological simulations, and those simulations were so big and so advanced that we had to use also a few computational scientists from ICM to help to get those codes running, and then to get the results transferred to different places in Europe. And also data visualization is another topic which is very, very closely related to cosmology as well. These are the main parts of the new computer center, which was shown here. So it's a new computer center where we have few systems. One of the systems that we'll use today is a Okeanos system, which is a system which is accessible for people or researchers doing large-scale computing. That means also many areas, but we have weather forecasting, which is using this supercomputer. We have cosmological projects, we have physicists, chemists, and many other researchers that use this supercomputer. Just a brief introduction, it has more than 1,000 nodes, each with 24 Intel Xeon cores. But for the more specific introduction, we'll go just in a moment for this. And then the other system is an Enigma system, which is dedicated to big data processing and analytics. If you are familiar with tools like Apache Spark, then this is a system which is totally for these kinds of tasks. So if you have a lot of data that you want to analyze with the new and modern techniques like Spark, then you can use this system. And there is also there are also some storage resources to keep the results of the analysis and of the simulations that are being run on the supercomputers. We also have some kind of a large-scale visualization and rendering infrastructure at this center. So just to give you an idea how many of researchers use the center, we have like around 300 registers active, computational grants that are being run on the supercomputers at ICM. That's approximately 500 active users. Active means that they are submitting jobs to our supercomputers and getting the results from around 100 different research institutions, not only from Poland. That might be also interesting for you as well, that the ICM is open for collaboration also abroad. And the main, as I said, for researchers, our resources are freely available. So the main thing that we want to get from you is to get some acknowledgements for using our supercomputers, and this is what we are also asking. We ask the users for yearly reports, and they are they have to say how many publications they had, and over the last few years, the number of publications was around more than 200 publications yearly. How to become ICM's user? You can use this email address if you want, but I'll also give you, and that's the main address where you get a lot of information. You can also go for the web pages as well, but this is the fastest way to get information on how to use ICM resources. You will get very fast response there. Just to give you an idea how we split the computational time on the system, we have a new model for the supercomputer that you will use. The model is based on the 3 categories of grants. So for example, if you want to go just to test our resources and try to run your codes, whether you can actually use the supercomputer and whether it is, your project would benefit from using those supercomputers, you can go for a test grant, which is less than 20,000 core hours. You get less than 20,000 core hours for 6 months. You can apply for it everyone you want, and then you get the review is only technical review. It's very fast. It's like less than 1 week. Then, if you want to apply for more than 20,000 core hours, and below 2 million core hours, you have to go through a review of ICM board. That's the board which is composed of researchers from ICM. But you can also apply for this kind of grants everywhere you want. I mean, during the whole year. And then for the biggest grants, where the computational time that you apply is more than 2 million core hours, you have to apply for a special grant challenges grant. That's a call which we have twice a year, and then we have a scientific board which is composed of researchers not from ICM but collaborators of ICM or persons who already use our resources or persons that we ask to review the applications, the proposals. That's the main idea. Maybe something which might be a little bit not so easy to understand is what is the core hour. The core hour is just if you want to run a simulation on a single core and it takes 2 hours, then you are computing 2 core hours. But then if you want to use the whole processor which have 12 cores, then you have to multiply this by 12, yeah, right? So if you are computing 2 hours on the whole processor on the 12 cores, then you have 2 times 12 core hours. That's how we measure actually how many of our resources you want to use. And 2 million core hours is a rather big number, I would say. What do you think, Wojtek? Is it a big number for cosmologists?
Not anymore.
Not anymore. Okay.
But yeah, it's a respectable.
Okay.
Respectable number.
Now I will go for the Okeanos system overview. It is, as I said, I have a couple of slides about the Okeanos system. Most of them come from the company that produced the systems, from the Cray company. They have produced the slides for us which actually tells details and about all the features that the supercomputer has. But I will go rather quick through it. As I said, it has more than 1,000 compute nodes, and each compute node has 2 Intel Haswell processors. Each processor has 12 cores, so you have 24 cores per node. So the node, you can see a node as a single computer which is like a PC computer, and then it is connected with other nodes through a network. Okay, so usually the nodes in the supercomputers that you see around the world now, you have nodes that are composed of few processors and have some number of RAM memory, probably more than 100 gigabytes, but might be also close to a few terabytes of memory. So this system has, as I said, 2 Intel Haswell processors, so 24 cores, and 128 gigabyte RAM memory per node, so per a single computer. It's very important to remember this notion of a node, because we will then use it when we want to apply for resources to run your jobs. You will have to use this terminology. And the one specific thing that this supercomputer has is also something which is called the Cray Aries network. That's some kind of a specific connection between the nodes of the supercomputer. You can connect the nodes just simply in a simple topologies, but this kind of network has a special topology I will just cover very quickly, and has some special features that can help sometimes to speed up the computations, parallel computations. How you interact with the supercomputer. Actually, as I said, there are many computational nodes, but there are some specific nodes that you use to log into supercomputer and that you can use to speak with the computer, to submit jobs on this computational node. So we have some special nodes which are called login nodes, which are where users actually access those nodes and they can do their work there. So they can prepare, for example, their jobs, they can submit their jobs, they can get the results. At the Okeanos systems, users cannot log into the compute nodes. That's not possible. You can only use the login node and submit the jobs to the computational nodes. And then one other specific thing about the supercomputer is that if you look at the system, if you will be somewhere in Warsaw one day, you can come to our center. You can see the system. Actually, if you open the racks of the system, you will not see any disks in it, because there are separate racks that have all the storage installed in this. So, like you see, the file system is actually when you look at the system here, these are the computational racks, and the file system racks are over there, somewhere at the end of the corridor. And actually, this is connected to the computational system through a network. So this is a network file system, which is a parallel network file system, which is accessible to all nodes, computational nodes, and also to login nodes. So you see all the computational and login nodes have the view of the same file system. That's quite important for running jobs as well. I will skip this. It's just I just said that you have login nodes, computational nodes, and there are some service nodes which I will not cover here, because they are just important from the point of view of administrators of the system. Now, the building blocks of the system. So the first element is something which is called a compute blade, and the compute blade has 4 compute nodes. Okay, so on such a plate, you have 4 compute nodes put very close to each other, and then 16 of these computational blades form something which is called a chassis. So you see a chassis here. You have 16 of those compute blades which are located there, and then each rack of the system has 3 chassis, and then the next important element of the building of this system are 2 racks, because 2 racks are connected with each other with a very good network connection. So you have very good network connection on the level of chassis, then also very good network connection on the level of 2 cabinets, so 2 racks, so 6 chassis, and then those pairs of racks are then connected with a little bit, I would say, not so good network, but still a very, very nice connection, so an active optical network. So the thing that we will have here on those 2 racks, I will cover it in a moment. There are special chips from Cray that are looking at the network and how it is used for computations, and can do some special things just to speed up the computations, parallel computations. You'll see in a moment. Okay, that's just.
So Okeanos is only 3 chassis.
So Okeanos is 3 groups. So it's 6 chassis. 3 groups, so it's 6 racks. 6 racks. Okay, so again, a computational node. Quite an important information here is that a computational node consists of 2 processors and RAM memory. And the memory is connected, is divided into 2 something which is called NUMA nodes. So we have 128 gigabytes, but this is split in half. So 64 gigabytes are connected directly to one processor, and the other 64 gigabytes are connected to the other one. And then between those 2 processors, we have something which is called Intel QPI, so Quick Path Interconnect. So something which connects the 2 processors between them. This might be crucial if you go really deeply on the optimization of your application. It might be crucial to look at those things. Here I just only tell you that this is something that you might want to look at if you go deeply into a single node performance of your application, because sometimes it is important to look at where you put your memory actually. So if you are, for example, if a process which is running on this processor uses a memory which is located here, it must go through the QPI, so the memory bandwidth is not so high then. So it means that it might actually have bad performance, comparable to a situation where you use the memory which is located in the same NUMA node. Okay? And there are some techniques that you can actually tell the system where the process should be located, on which processor. So then you can say that it should be located in a specific NUMA node, for example. Okay. Now this is another view of the memory. I will not go through here. It's just a view of the board. You can see that here are two nodes actually. So this is one node, the second node. Here you see the processor, two processors, the other two processors, and also the memory here, right? Memory is located over here. And then two of these daughter cards are located on the something which I already say that it's called the computational blade. Okay, so this is the computational blade. It consists of two daughter cards, each with two nodes. And then an important thing is that such a blade has something which is called a Cray Aries interconnect chip, which is a special addition from a Cray company, which is a chip that controls the network movement between blades and between nodes. I will show you in a moment how it can actually be used. So you can see here there are those 4 nodes connected to one Cray Aries chip. Okay, so this is one Cray Aries chip per compute blade. And then you can see also from here that this Cray Aries interconnect have some special cable routings to different ranks of the memory. So for example, here the first rank, the rank number 1, is a connection between all nodes in a chassis. Okay? So the green one is the connection between all nodes in the chassis. Then the black one is a rank 2. That means that it's a connection between 6 chassis. So the connection between chassis and nodes in 2 racks. Okay? And then if you go further, you have a special routing cable here. So rank 3 is used to communicate with nodes that are located in other pairs of racks. This is the topology of connection inside the chassis. So it's all-to-all. So each node has a direct connection to each other node in the chassis. Okay. You cannot actually do it on the whole system because the system is composed of 1000 memory. It would be impossible. It would be very expensive, and usually the companies that produce the supercomputers, they are looking, and also people that build those supercomputers, they are looking for some different methods to connect those nodes if you get to really big numbers. So here you have a direct connection of all the nodes inside one chassis. And then if you look at the other chassis, so you have here 6, so those yellow lines here, each one represents a single chassis. Okay, so you have 6 chassis, so that's the rank 2 interconnection. And within this, you have a direct connection between Cray Aries chips. So so for example, here you can see that the first Cray Aries chip in this row has a direct connection to all other first Aries chips in other rows, so in other chassis. So that forms actually a structure of rows where you have a direct connection between all Cray Aries chips in a chassis, and then you have columns which are composed of those connections between first, second, third, and so on RS chips in a chassis. So now, how to, of course, if you are running parallel computation of such a system, we'll go later on. We'll see how to run those simulations, and then you will actually know that those simulations run with a very big number. Usually, they run with very big number of processes. Those processes are located on different nodes. And the main thing is that they have to communicate with each other, because all the processes, they are doing their own work, but also they have to tell what they are doing to the other processes, for example, and exchange some information with each other. So, for example, for the cosmological simulation, it means that usually if you have a lot of particles around in a three-dimensional box, they are first distributed to different processes, to different nodes. But then when the simulation goes on, there might be a situation that you will have to communicate some information with other processes, for example, to say that these specific particles influence the behavior of other particles that are located in some other processes or some other nodes. So then you have to send messages between those nodes, between those processes. Then you are using network, and then you are using those connections that you see here. So just to give you an idea how this Cray routing can actually be used, is that sometimes, so for example, you can, if you look at these connections here, you already see that if you find two Cray RS chips here, for example, one over here and the other one over here, then the minimum number of hops between them is always 2, right? So you can go like this, so move in a row and then in the column. So that would mean that actually that would be the shortest path to send a message, you know, to use this kind of routing that you send from here and you receive here. So you just send like this and here. But sometimes it might happen that this specific Cray chip is already used by some other processes, and it has a lot of work. And then this Cray interconnect can actually, so the Cray RS chips can actually see that the red here means that it has a lot of work to do. So it's not very efficient to use it now to transfer the information to this receiver here. It's better to send it through a different path, and you can actually, this interconnect can choose a different path which is not a closest path if you look at the topology, but it will be the fastest path if you look at the time for sending a specific message. So that's the thing which is behind this Cray interconnect. Here's just a view of this rank to cabling of two racks. And then what I said before, you have those groups of rank 2 connected with the rank 3 between them, with a specific number of ports that you can use. So like 240 ports are available for 2 cabinet group or 2 rack group. So and the last thing that I have here is just the view. If you are interested on how to cool down such a system, you have actually 2 options. The one option is to use the water cooling, and the other one is to use air cooling for the machine. If you have such a big number of nodes and processors in one rack, that it can get really hot. That means that you really have to find a nice way to cool it down. And in the Okeanos system actually is using the room air or the air cooling. It means that there are some blowers here located between each two pairs of cabinet. And so the air is blown from here, then it goes, it's a cold air, then it goes through the machine, it becomes hot, then it's getting cooled down over here, and then blown through the other pairs and so on. Okay. So now I will go to Okeanos user's environment. I will try to describe some of the specific things about the user environment that will be important for you. So first of all, system access and data transfer. That's a I don't know, maybe some of you seen the Martian movie. That's a movie about an astronaut which becomes stranded on Mars, and then he tries to come back on Earth. And there is a student which is actually trying to find a way to get him back from Mars. And there is actually some truth behind this. The things that he was doing is that he was using a real supercomputer. He was using a Pleiades supercomputer, which is located in NASA laboratories. But there was also some kind of, I would say, not true information on how to use those supercomputers. He was wearing a jacket and sitting in a computer room with his laptop, connected with the supercomputer. That's not how you're going to do it. It's you can use it from your home, you can use it from your hotel, you can use it from here. You can connect with it through network, and it's. And you will also not see this calculation correct. Unless you program it with your own software. Yeah. Okay, so how it is organized at ICM? When you do it from home or from hotel, for this specific lessons and for the workshop that we will have, we have a more direct access to the Okeanos supercomputer, so you just have to log into this Okeanos supercomputer. But usually, after the workshop, you will have to use something which is called a login node, the main login node to ICM login node, which is called hpc.icm.edu.pl. So you use the SSH protocol to log into the system, and then you have access to all the supercomputers that are located at ICM. One of these supercomputers is Okeanos. But for the workshop, you will see that we will log in just directly to Okeanos. It will be much more, it will be faster, and we will not have to go through some of the difficulties of going through the login node. So as I said, you use the SSH protocol. If you are a Windows user, then you can also find some kind of tools to use the SSH. So the software is called PuTTY, and then you just run it. You can just put the information about the system, normally logging with your username and with password. On a Linux and Mac, you can just use SSH in your console. So for the workshop, we'll use, as I said, direct access to the supercomputer. So it's okeanos.ocean.icm.edu.pl, but we'll come back to this during the workshop as well. So you just SSH to this machine with your username. You will get a username, and you will try to log in, then to do some work there. This is just a slide. You will get those slides probably. So this is just a slide how to do it on the Windows system. Yeah. Then on the newest Windows systems, you can actually use as well the PowerShell, and it actually works.
Just a side comment. In the workshop, we'll be using local computers with Linux.
Okay.
So
yeah.
But later, if you would like to do it in home, you can.
Yeah, it's, as I said, it's only for.
I guess there's no reason to do it in Windows other than it's possible.
Yes, yeah. Of course, we'll do it in Linux during the lessons. How many of you are familiar with Linux? Maybe that's a question of. Yeah, with Linux. Okay.
Or Unix.
Or Unix, or.
Great.
Okay. We'll come back to it later as well. But for the workshop, you don't need to have the knowledge of many comments. So if you have problems with, you can just ask us, and it will be like a few seconds to describe the comments. The most important comments that I wanted to give you here are so that you have to remember this SSH comment that you will use to log into the system, and also for the data transfers. you have to use the commands like cp is a command to copy files between For the copying files between systems, Linux systems, you use something which is called scp, so it's secure copy. And you use it in a very similar way as with the copy command, but you give so the name of the file, local file, and then you give the location, remote location that this file should be copied to. So for example, you give the username at which system, and then you define which directory to copy to. Of course, you can do it the other way around as well. We'll go through it again during the workshop. I don't go through it now. Again, if you are a Windows user, you can find the tool which is called WinSCP, which can actually do the same, but with the use of Windows. Yeah. Okay. Now we go to the queuing system. So we all know about queues, right? But so the nice thing that was with those queues is that actually you could ask somebody, you can hire somebody to stand in a line for you. You can go to sleep or go to do some other things, and that's something which I find nice as well with the SLUR queuing system. Most of the times when I try to describe on how you can use supercomputers is that you don't have to sit with your computer and look how the simulation is going on. No, you just submit the job, you can go home, right? You can sometimes you have to wait for resources, but for example, during night, it might become a situation that the resources will be available, and then your job will start, and it will just start computing.
But it would never work in the British queue, so British would never allow this. So this is purely communist area invention. So let's say supercomputers have something from the communist area.
Yeah. Yeah. Okay. And then what I wanted to describe here is the SLUR is one of the queuing systems available. It's actually kind of a software that is being installed on a supercomputer. There are many others. There are, for example, PBS system or almost all the vendors. They also so the companies that produce supercomputers, they also have some. For example, IBM has their own queuing system. But the SLUR queuing system is one of the most popular, together with PBS. It's one of the most popular ones, the most popular ones. So it is also popular because it's under the GNU license, which is quite nice. You can also pay for a specific service for this SLUR. So there is a company which is called SCATMD, which you can pay them to provide support for you. But if you don't want support, if you want to do the support by yourself, you can just download it and use it on your Linux cluster. So at the Cray system, we are using SLUR. So the main features are that it can be used for allocation of specified resources, so computational nodes for exclusive or non-exclusive use. Here at the Okeanos system, we have only the option of an exclusive use. So it means that if you are applying for a node, this node will be exclusively for you. You cannot share it with other users. Okay. It can be used to run, of course, and manage parallel tasks on allocated resources. So you can define your job, you can submit your job, but then you can also check the status of your job, and then also see for example, the history of your work on a supercomputer. You can see how many jobs you have been submitting. You can also see how many core hours, which I described you. You can see how many core hours have you already computed on the supercomputer within a given time frame. And then queuing of computational jobs. You will see it in a moment how actually it works and can be used. So the main terminology that you should be aware of is first of all, the most important one is that you have in the systems you have nodes. So it is a single cluster node on which you can allocate resources. Then a partition, it's the set of nodes on which jobs are queued. For example, those partitions can define a different, they can define the parts of the cluster that are that can be used for different kinds of jobs. For example, one partition might be a specific partition for short jobs, and the other partition, so the set of nodes, might be a specific partition for longer jobs or bigger jobs in terms of number of nodes, things like that. So that's the thing that administrator can actually use to somehow distinguish the parts of the cluster that he wants to give to different users. Then he can also manage and also define which users have access to which partitions. But for the sake of this workshop, we will not go through this because there is a single partition for us. Then you have job and job steps. A job is a set of user programs with resources and potential relationships. So we have, you can define a job. To define a job, you have to say that how many nodes you want to use, for how long you will use those nodes. Sometimes on some Linux clusters, here it is not important, but sometimes you have to also define the number of memory that you will use. And then there are some other specific parameters that you have to define related to some specific features of the system. But we'll come back to this during the workshop. Here are the main commands of the SLUR system. So, for example, salloc is a command which allocates nodes and other resources for the user tasks. So you can use this salloc mode for doing some kind of an interactive job. I will show you. We will be talking about interactive mode, and we will be talking about batch mode. So interactive mode is a mode where you can apply for resources and work on these resources interactively. For example, run one short job, then check the result, run another, and things like that. In the batch mode, it's a little bit different, because in a batch mode you create a specific script which describes your job, you submit the script, and you go home. Okay, and this batch job will be queued. It will wait for resources, and then it will be executed by a SLUR system. For example, here is one of the examples how you can use the S-batch. You can use the S-batch with by saying how many processes you will use minus N4. That means that you want to run 4 processes, and then you give a specific script. It's called the queuing script in our terminology, which defines the other parameters of the job. Then if you send if such a job to the queuing system, you can also work with those jobs. So, for example, if you decide that you want to cancel the job because you made some kind of a mistake, you can just cancel it by saying a scancel command with a specific job ID. We'll also come back to this during workshop. You have to try to cancel your own job. Then you can also, for example, ask. One of the most important commands is the sq command, which actually display the state of the job queue. So you can see all the jobs that are currently running on the system. And then another important command is the srun command, which launches the parallel task. So if you are applying for 4 processes, then to run an application which will use those 4 processes and actually 4 cores, you have to use the srun command with the number of your with the name of your program and with the number of processes that you want to use. Okay, now we'll go through these modes that I told you. So the first mode is a pre-allocation mode, or so-called interactive mode. On this Okeanos system, it is a little bit different than on other systems, because here, as I said, you can only work on the logging node. So if you are using it, you are not going through a computational node directly. On some of the Linux clusters that you can work on, probably also at ICM, the interactive mode means that you actually go to work on the computational. So you log into computational node and then you do your work there. But here on the Okeanos system it's a little bit different. So you have to first allocate the number of nodes that you want to use. So with the salloc command. So you use the salloc command and you say, for example, that I want to allocate only one node. So this capital N, say that is the number of nodes that you want to use. Then, if you get those resources, you will receive a new shell on the logging node. On the logging node, not on the computational node. So all the shell commands will be also executed locally on the logging node. Okay? But then, if you want to run your program on the computational node, you need to use the srun command. Okay? So for example, if you have a program, then you use srun myprog or srun -n. So the number of processes is 24 because each of these nodes has 24 cores, and you specify the name of the program. What is nice about this mode is that you can do those srun commands multiple times. So for example, you can run a single short simulation and you see that there is something wrong with your input file. So you don't have to submit the whole new batch job to the queuing system, but you can change something in your file and then submit the program again very, very fast, and you don't have to apply for the resources another time. But you can interactively change something and try a few times to for example, fix something in your scripts. One important thing, and you will also see it during the workshop, is that after you have used such the supercomputer in such a mode, in pre-allocation mode, you have to close the session. That's very important. So if you close the session, you release the resources. Okay, so the moment when you allocate the resources, you get the resources and you get a special shell. You work in this shell, and then if you want to free the resources, you say exit, and then you free it, and you are coming back to a shell that in which you have been applying for resources with the salloc command. The other mode is a batch mode. So the one that I told you that you can use it if you want to define your program, the parameters of the program in a script file. You are submitting it to the queuing system, and then you can go home. Actually, the queuing system will take care of your job. So if you already know that your job is prepared nicely. For example, you have used interactive mode to check a few things, and then you are ready to run your job, which will run for 2 days, for example. Then you can use this batch mode. So in the batch mode, the system allocates specific resources and runs the sequence of commands described in the script. Okay, so in the script you have not only to define how many nodes you want to have, how much time you will use it, but also you have to define all the commands that will be executed. So the commands that define the computational job. The script must have a given structure. I will go through it just in a moment. You don't have interaction with the running program, right? So you can just only see what is the status of the job in the queue. So you can, there are some ways to control it, right? You can, for example, if you are developing your own application, you can, for example, define a file. If you put something in a file, then the application can look whether you have changed something, and then it can behave in a different way. I know that some cosmological codes have actually this. So you can stop the application by putting some information in a specific file, and then this can happen. But you don't have a direct interaction with the running program, and all the management of the simulation. So, for example, you cannot kill the simulation by itself, but you have to do it through the SLUR queuing system. And quite important thing is that, as I said, it has a given structure, and in the structure, the most important part is this hash sbatch lines, which define all the parameters of the job. So the SLUR parameters of the job. So here is, for example, an example that you can use sbatch command with a specific script. This script is can have such a form. You are first defining the what kind of a shell you will be using to interpret the commands that you will have in your queuing script. And then at the beginning, it's very important that it must be at the beginning, not somewhere in the middle of the script or at the end of the script, but at the beginning, after this definition of the shell, you have to put the lines of the SBatch and then define the parameters of the job. You can also give all of those parameters here on the command line to the SBatch. These are just actually arguments of the SBatch command. Okay, but it's much more easier to put all those things here and then use it multiple times. If you are running multiple simulations, you don't have to put this again here. Okay, so this is just a summary of what I have said. So the script file is a text file containing SLUR job parameters and script execution commands. Lines which start with SBatch define job parameters, and the rest of the script can contain any shell script commands which will be executed on the logging node. That's very important. Okay, that the shell script commands will be executed on the logging node, not on the computational nodes. You can put some comments which begin with hash, and then you can write the program execution commands with srun. Here is an example of a SLUR script. Parameters, so for example, you can give the specific job name, you can define the name of the file which will have the output of the program, the name of the file that will have the standard error of the program if the error occurs. Then you have to use the word which is called account. That means we are, so as I said, we have a lot of users, and those users are organized in grants, computational grants. They have their own Linux groups, and they have to use those Linux groups here when they write their own queuing scripts, because then later on we can actually do some summaries of how many core hours have been computed within a grant, not for a single user, but within a grant. So a grant can have multiple users. For example, it can be the whole laboratory, or a few people, for example, a professor and his collaborators. Then during those classes, during workshops, you also have to use this reservation, because we have a special reservation on the system, so you will not have to wait for the resources during the workshop, which is quite nice. We will have a reservation of 128 nodes on the system. Then you can specify the number of nodes that you need, the number of tasks, so processes that you want to run per each node, and how much time do you need to run your job. So for example, here we are applying for 1 hour. Okay, so it's hours, minutes, seconds. You can also apply for days, but we'll come through it later. And then inside the script, you can, for example, have a simple command, srun command, which will execute your program on 24 times 16 cores. Okay, so you want to have 16 nodes, each with 24. So you have to multiply this number to get the number of cores and number of processes that the srun command will run. And quite important information here, the srun command, it already knows about how much nodes you have been applying for and how much tasks per node you have been applying for. So there is no need here to put on the Okeanos system. On other systems, sometimes it might be necessary.
It's specific, it's Okeanos specific feature.
Yes, I would say that it's kind of configuration of SLUR specific. And in Okeanos, it just works that srun understands how many.
It's a good practice to suggest to compute this number yourself and specify anyway. So
many users do it, because then you can use the script on other systems as well. Yeah. So as I said, this is just a short summary that you can apply it for nodes, number of tasks per nodes, or number of tasks in total. If you apply for number of tasks in total, then the system, the SLUR, will decide by himself how to put the processes on the system. So for example, if you apply for 25 processes, it will have to use 2 nodes, but you will not have control on how to distribute the processes between those nodes. So it's better to, for me, actually, I always use this number of tasks per node. Yeah, so this is much better to use this than number of tasks. Then if you are running some hybrid programs, we'll come back to it later tomorrow actually, what are the hybrid programs, but sometimes it is necessary to also specify how many physical threads should be assigned to each process. And we'll come back to it later, but that's just, you have to remember that there are some things like that. And if you are familiar with hyperthreading, so interprocessors have the hyperthreading feature, which means actually that on this specific processor that we have on the Okeanos system, it means that each physical core can support up to 2 threads. So there are threads that can use one single core. So actually, if you are running an application, you can actually specify, for example, 48 processes that will run on the node, not 24 but 48. The HT mode, so the hyperthread mode, is enabled on the Okeanos system. If you don't want to use it, and there are many situations where you don't want to use it actually, then you have to put this information. So it's no multi-threading. A quite nice feature about SLUR is that when you made a mistake in your job and you want to correct it, you don't have to cancel the job, but you can also use the S-control tool to update some of the parameters of your job. So here, for example, you have a command which updates the time limit for a specific job ID. So you can say that this specific job will be 10 minutes longer. Of course, this only works when your job is in the queued state. If it begins to run, then you cannot change it, right? So it's because it would not be. Otherwise, you just apply for 1 second and then you would change it to 4 days, right? So it doesn't work like this. So for example, with this command, you can add 10 minutes. But you can add more or subtract more, subtract or just override the time limit. So, for example, here I said that I will come back to see what is the actual time format. So, if you just put one number, then it's minutes. If you put 2 numbers, then it's minutes, seconds, then hours, minutes, seconds. If you want to give days, then you have a number of days, then minus, and you put, for example, hours, or days minus hours, minutes. So that means that, for example, if you put 2 minus 10, then 0, 0, then it means that you want to use the system for 2 days and 10 hours. Okay, and ID here is something which is called job ID, and it is something which can be returned by the SQ command. So the SQ command, as I said, is a command which lists all the jobs that you have on the system. Quite a nice thing that I have discovered not so long ago, which might be useful, is a SBatch option which is called test only. So, for example, if you want to check when your job will start, if you apply for a computational time of, for example, 1 day, it might result that you have to wait for, I don't know, 2 or 3 days, because there are a lot of users that already are using systems and they are in the queue as well. So you can use this test only option just to ask it. So you can use SBatch with the test only option. It doesn't submit the job to the system, but it reads the parameters of the job and tells you when the job will be started if you submit it now. Okay? And that's quite a nice option. Also, for example, in situations where you can decide to run your program on a less number of nodes. For example, you can use it on the 64 nodes, and it will be much faster than on 32 nodes. But you want to start the job immediately, then you can decide to lower the number of nodes just to have the work started immediately. So that's quite a nice option. Actually, I think that's something that might be very useful to run simulations as well.
And I just learned about it now.
Yeah, I learned about it also quite lately. I think it's very useful. Okay. There are also environment variables that are available for inside the SLUR job. It might be useful for you if you, for example, want to use some kind of a processing of the number of nodes that are available for computations, or the number of tasks that you are using. Those environment variables can be used inside the script or in the interactive mode as well. So, for example, if you want to write a script which can be used in general cases when you submit jobs on different number of nodes, you can use those environment variables to ask within the script how many nodes we are using. So, for example, to prepare the number of files that had to be prepared for such a simulation, something like this. So that's you should know that you can, from within the script, you can ask about most of the parameters of your job through the environment variables. And also for advanced users, you can also define dependencies between jobs. If you want to run multiple jobs, for example, that have some dependencies, you can start the second stage of the job after the first stage is completed. Then you can define those dependencies in an SBatch or SRun option. So those dependencies can say, for example, that you will start the specific job that you are submitting after the start of a given job or jobs. Yes? So if a given job starts, then I want this job that I'm submitting right now also to be started. Then, for example, you can say that that your job should start only if a given job or given jobs end without errors. So if the first stage ends without errors, then I want to start the other jobs as well.
How this is recognized, if I can ask? How this is recognized, if error occurred or not?
So this is recognized by a signal that is that SLUR actually manages as well. So there are many options that can be used here and types of dependencies between jobs. But not, I think most of the users don't use it, but if you would be interested in it, then it's another thing that you can use. Okay, now we'll go to software modules. On the Okeanos system and also on other systems at ICM, we are using something which is called environment modules. That's a tool to actually gather all the settings of a specific, for example, of a specific application. You have an application installed on a system in order to not to remember the path of the binary, or for example, not to remember the types of environment variables you have to set to use this specific software. You can pack this into something which is called module, and then before you want to use this software, you can just say that you want to load this specific module, and then you will see it in a moment how it actually works. For example, inside such modules, you can define the path, man path, or for example, license of some of the software that use licenses. For compilers, tools, and libraries, it can be even more. So, for example, you might specify the paths of the the loading library paths and other things. The module commands are, the basic ones are, so module avail will list all the modules that are available on the system. So for example, all the software that is installed on the system. Then you can list, so module list is the list of modules that are currently loaded in your environment. So the modules that you are using currently. Then you can load a specific module, for example, with such a command, module load perf tools is a module that is available on the Okeanos system. Or you can also swap modules, so replace the modules. So for example, this is a kind of good example, because on the Cray system, the programming environment is packed for each compiler families separately. So for example, we have a programming environment for the Cray compiler family, and then specific programming environment and module for the GCC, so GNU compiler family. The Cray compiler family is default, so if you log into the system, you have it already loaded. But sometimes it's better to use a different compiler. For example, if your application needs a GNU compiler, then you can use this command to swap the programming environments. We'll also have this on in one of the examples during the workshop today. Okay, I'll say that this is, I already said that. Okay, do you have any questions?
Thank you very much, Maciej.
Okay. Thank you.
Thanks for actually finishing a little bit before the time, which will give us a chance not to shorten the coffee break too much, and enough time to move
to the
workshops. Yeah. So any questions so far? Yes, it wasn't very packed scientifically, but technically, so I guess you still need the time to digest it. So don't worry, you don't need to memorize all of these comments, because we'll walk through them we'll walk you through them during workshop. So if there are no other questions, I guess let's have a coffee now. And instead of going to the workshop 4:45, let's go to workshop to the laboratory 3:30.
Okay.
Thank you.
Thank you.
And where is the laboratory?
Okay, this question is not easy answered because it's not very trivial to go there. But our colleagues organizers have put arrows. It would be best if we, let's say, meet here at the coffee area 25 past, and then you can follow us. Because you can really go up and down and around a little bit. Oh, by the way, don't forget.